Unit 5.2 notes, analyzing graphs of polynomial functions. So first we're going to look at the parent function of a cubic and the function x to the fourth. So for the parent function of a cubic, we are going to take these x values and we are going to cube them. So we have -2 cubed, which is -8, -1 cubed, which is -1, 0 cubed is 0, 1 cubed is 1, 2 cubed is 8, and 3 cubed is 27. Notice that this parent function of a cubic crosses through the origin at 0, 0. Okay. Then we have the function y is equal to x to the fourth. And so for this parent function, we're going to take all those x values and we're going to raise it to the fourth power. So we have -2 to the fourth power, which is 16. -1 to the fourth power is 1. 0 to the fourth power is 0. 1 to the fourth power is 1. 2 to the fourth power is 16. And 3 to the fourth power is 81. So notice here, a cubic function has an odd degree. Since the degree is odd, if we cube a negative, we get a negative, okay? Versus an even degree of x to the fourth, if we take a negative and raise it to the fourth power, we're going to get a positive. This is important to note because of the end behaviors here. So on an odd degree, notice how the end behaviors, those arrows on either side, are going in opposite directions, while the end behaviors for the x to the fourth parent function are going in the same direction. Okay, now we're going to look at the rules of transformations, and as we're going through these, you're going to notice that these are the same as when we were doing transformations of quadratics. Okay, so going through A, if A is greater than 1, we say this is a vertical stretch. If A is less than 1, this is a vertical compression. And if A is negative, we say this is a reflection over the x-axis. For B, if B is greater than 1, this is a horizontal compression by the reciprocal. If B is less than 1, we have a horizontal stretch by the reciprocal. And if B is negative, we have a reflection over the y-axis. Okay. Note here that if we don't see a B value in our equation, we assume B is 1. Okay, so if you don't see B, then assume B equals 1. Okay, then we have our C value. So I'm going to go ahead and highlight this whole expression, x minus C. So if we have x minus C, this is telling us that we are going right. X plus C is telling us we're going left. And then lastly, D, if we have a positive D, it's going up. If we have a negative D, it's going down. Okay. And if you do not see a C or D value, so I'm going to write a little note here again. So if you don't see C or D, assume it's 0. Okay, so let's look at these examples here. For example 1, we're going to first label our A, B, C, and D. So A is 1/2, B is 1 since we don't see a B value. C, I'm going to write the whole expression, x plus 3, and D is 5. So this tells us that we have a vertical compression. So a vertical compression by 1/2. The B equals 1 does nothing. X plus 3 tells us we're going left 3. And D equals 5 says we're going up 5. Okay, example 2. Our A is -1. Our B is 2. Our C is X plus 5. And our D is -1. So this tells us we have a reflection over the x-axis. B equals to 2 is greater than 1, so we have a horizontal compression of 1/2. X plus 5 tells us we're going left 5, and -1 tells us we're going down 1. Okay. Example 3, labeling our A, B, and C. So A is 2, B is -1, C is X minus 4, and D, notice we don't have a D value, so we assume it's 0. Okay, the A equal to 2 says we're going to have a vertical stretch by 2. B equals -1 says we're going to have a reflection over the y-axis. X minus 4 tells us we're going right 4. And D equals 0 doesn't tell us anything, so we can skip it. Okay, and again, I found 1, 2, and 3 based off of my definitions up here. Okay, following all those transformation rules. Okay, now we're going to look at number 4, where we're comparing the parent graph to the new graph. Okay, so right here, that dotted line is our parent graph, and the solid line is the new one. So first, I'm going to point out that, remember, we said that the parent function crosses through the origin. So where it starts to curve is that point 0, 0. So if we were to do where it starts to curve here, that would be this point. And so we would see that we started at 0, 0, and then we transformed to -4, -2. So right away, this tells us that we went left 4 and down 2. But notice how this part right here looks a little tighter and compressed compared to this part that looks a little bit stretched out. So because of that, we say that this had a vertical compression. And we're not able to say by what, because we're not given any other data besides just looking at our graphs. Okay, example 5. We're comparing our parent function, so that dotted line there, to our new function. Okay, so we started at the origin 0, 0, and it looks like we moved to 2, 1. So 0, 0 to 2, 1. This means that we moved right 2 and up 1. But notice that if we were to take our original function here and flip it, it looks like that this got reflected across the y-axis. So we have a reflection over the y-axis. Okay, next part. Okay, so this part is the only new part of this notes, is the increasing and decreasing intervals. So when we think of increasing and decreasing intervals, I want you to, we're going to write a little note off to the side. We're going to think back to Algebra 1, okay, when you guys learned about linear functions. Okay, so remember when you were graphing linear functions, we had a positive slope and we had a negative slope. Okay, we had a positive slope and a negative slope. Well, I want you to think in regards to the same thing, but instead of saying positive, I want you to say increasing. Instead of saying negative, I want you to say decreasing. Okay. So in order to determine which of these intervals are increasing or decreasing, we have to first separate them into intervals. And notice here, at the turning point of each of these points here, you saw how it's starting to go down and then it goes back up, start to go up, then it goes back down, starts to go down and goes back up. These are our separators between our intervals. So we have this first one, this next one, this third one, and this fourth one, okay? And if we look at each of these colored lines individually, we're able to see what type of slope it has. So the pink one is going down. It has a negative slope, so we say that this is decreasing. Okay. The green one is going up. It has a positive slope, so we say that this is increasing. The blue is going down, so we say this is decreasing. And the yellow one is going up, so we say this is increasing. Okay. So now that we've identified each of our intervals, we're going to now write them versus increasing or decreasing, whether they're increasing or decreasing. So starting with increasing, notice our first increasing one was the green. So we have to look at the starting value of the x's versus the ending value of the x's. So it looks like our starting value is around negative 2.7 and our ending value is around negative 1.5. Okay. And then we look at our next increasing one, where again we're looking at the x value where it starts and where it ends. We have about 0.4 to infinity because of that arrow. Okay. And remember, when we're connecting two intervals, we have to use the union symbol to connect them. So those were our increasing ones. Our decreasing ones, starting with the pink, notice we start at negative infinity and we go to right before that green one, which we said was negative 2.7, union with our other decreasing variable, which is the blue, and we start at the end of the green one, which is negative 1.5 to 0.4. And again, let me highlight all of these so we can see. So this is the decreasing, increasing, decreasing, increasing. Okay. So that's what we're going to do for these examples here. So on example 6, again, we're going to label all of our intervals. So we have this one that's decreasing, this one that's increasing, and lastly this one that's decreasing. Okay. So looking at the one that's increasing is the green, we can say that the starting point for that at the x's is negative 0.2 to 1.5. Okay, we only have one increasing interval, so we just leave it as that. We don't have to add in the union symbol. Okay, and then we have two decreasing ones. So starting with the pink, it starts at negative infinity on the x's, goes to about negative 0.2, union with the blue part, 1.5 to positive infinity. So I know it looks like it's going towards negative infinity, but we have to remember that we are only looking at the x's. We are not looking at the y's. So since it's going to the right side of the x's, it's going to positive infinity. Okay. And then looking at the domain and range of this function, since we have arrows going in either direction, we would say our domain and range are both all real numbers. Okay. Example 7, I'm going to do the same thing and start separating them. And then I'm going to be labeling my intervals that are increasing. So my increasing one is that pink. It's going from negative infinity to negative 1, union, and then I have my blue, 0.2 to 1.5. Okay, and then my decreasing one, starting with the green, I have negative 1, 0.2, union with my yellow, which is 1.5 to infinity. And then the domain here is still all real numbers, but our range, notice how it stops up here at 3. So we would write that this is negative infinity to 3. Last part here is the end behavior of a function. So when we're looking at the end behavior, we're looking at what the endpoints, those arrows, in which direction they're going. So for example, if we have x goes towards negative infinity, that's the left side. We look at this endpoint here because it's the closest, and since it's going down, we say that this is going to negative infinity. Same thing as x approaches positive infinity, as it goes to the right direction. This is the endpoint that is now the closest, and since it's going up, we say that this is going to positive infinity. And since we have arrows going in different directions, we would say that our domain and range is both all real numbers. Okay. So on our examples, they do not have it set up for us labeling as x approaches negative infinity or as x approaches infinity. So we have to do that ourselves. So on number 8, I'm going to set it up as x approaches positive infinity, f of x approaches, and as x approaches negative infinity, f of x approaches, and then do my domain and range. So these arrows right here stand for approaches. Okay. So let's start with as x approaches positive infinity. So as it goes to the right side, we look at the endpoint that's closest to us, and this endpoint is going up. So it's going to go to positive infinity. And then as x approaches negative infinity, going to the left, we look at this endpoint, and this endpoint is also going up. So we say that this is also going to positive infinity. Our domain, looking at the x's, is going in either direction, so we say this is all real numbers. But our range, notice how it stops right here a little below negative 2. So I would say that the range is negative 2.2 to positive infinity. Okay. Same with number 9. I'm first going to set up my my question. So as x approaches infinity, f of x approaches, as x approaches negative infinity, f of x approaches, and then my domain and my range. Okay, so looking at positive infinity, that's going to the right side. As I go to the right, I look at the closest endpoint, which is this one. It's going down, so I say that it's going to negative infinity. And then as x approaches negative infinity, it's going to the left. So I'm now looking at the endpoint that is now going up. So we say that as x approaches negative infinity, f of x approaches infinity. And since our arrows are going in separate directions, in all directions, we would say our range and our domain is both all real numbers.